Hello, my name is Carlos Matallana. I'm the protocol team lead at Polygon zkEVM, and today I will be talking about our idea in order to do data compression in rollups. Okay, in this presentation I will just do a very quick introduction about how we put data in layer 1 today and what we think it could be a good option in order to reduce this data availability to be added on layer 1. Okay, first of all, how do we put this data availability on layer 1? So basically we have a smart contract call which is called sequence batches, and basically here we are just adding a sequence. What's a sequence? A sequence is a set of batches. And what is inside a batch? There are transactions. And how do we encode those transactions in order to add it to layer 1? So basically what we do is we do the LLP encoding of the Ethereum transaction data, and then we concatenate the signature at the very end. You will notice that the LLP of the transaction data is basically the message hash, the one you sign. This is very convenient to us because then inside the circuit, inside the zkEVM ROM, you literally has the message hash, so it's very quickly to do the easy recover. Okay, now we're going to see which are the different fields that affects a layer 2 transaction host. The first one is data availability. The data availability, basically you just pay for each byte that you put on chain. Then you have the sequencing. The sequencing is basically a constant cost when you call the smart contract call that I showed at the very beginning, the sequence batches. So it has a constant call because, well, you need to do some memory expansion, you need to do some hashing, and you need to do some storage, some data on the smart contract. Then you have the prover. The prover is like this specialized hardware that you spin up, so you need to compute a proof for each batch. And of course, this has a cost associated. And later on, when the prover just computes the proof, then you send the proof to layer 1, and then when you send the proof to layer 1, you need to verify it. So you need to verify a snark, and this verification is not cheap in Ethereum. Okay, but since we are using recursion, this cost of verification is shared among all batches, all transactions, all sequences that we put on chain. Basically, this is a summary, just in order for you to check that currently the most important field that affects to the layer 2 transaction cost is the data availability. That's why we're working hard in order to reduce this data to be put on chain. Okay, and in order to do that, what we are going to do? So first of all, we're going to remove signatures. Signatures are 65 bytes that currently they just go directly on data availability on chain, and it costs money. So in order to remove those 65 bytes, what we are going to do is a proof that takes all the signatures and verify all the signatures. So basically, you just remove all the signatures of all the transactions, and instead of that, what we are going to put on chain is a snark proof. And later on, inside the circuit in layer 2, we will verify this snark, which basically verifies all the signatures. Then we remove the signatures, the concatenated signatures at the very end. So what we want to do now is to kind of reduce the data regarding the first part of the transaction, which was the LLP encoding. In order to do that, we're going to use a very small set of functions in order to reduce these bytes that we put on chain. In order to do that, we're going to introduce two new data structures. They are basically sparse Merkle tree instructions. The first one is the address tree. You can see the address tree as a mapping between an Ethereum address and an index, a short index. So instead of having 20 bytes, we will have just 1 byte in order to refer to an Ethereum address. And the same happens with the data tree. The data tree is just, you can imagine, as a mapping between 32 bytes and an index in the Merkle tree. Okay? Okay, so let's see all the functions that we define in order to do this data compression. There are just 8 functions. In order to define 8 functions, we only need 3 bits. Okay, so the first byte, the most significant 3 bits, will be like the definition of the function. Later on, it's remaining 5 bits, which will indicate something to do with the following bytes. So the first one, for example, is how to encode 32 bytes, less than 32 bytes. So we first have the function, 000, and then what we call the header payload will indicate how many bytes to read. So here the question is, of course, what if I want to read more than 32 bytes? So this is kind of exactly the same as the RLP encoding. So in the header payload, what we encode is the length of the bytes that we are going to read. Those are kind of straightforward, simple. Then we have the small value function, which is basically, in order to encode a small value, we can encode directly in these 5 bits of the header payload. Then we have, and this comes the really compression, we have the 32 bytes compressed function, which is basically, in the 5 bits, we set how many bytes are we going to read, and these bytes that we are going to read, it will be the index in the data tree. And the same happens with the address. The bytes that we're going to read will be the address in the address tree. So you can do the mapping between an index and an address. Then, well, normally when you do a transaction, there is this kind of value gas price that from time to time you just put a lot of zeros. So in order to skip this kind of encoding, you waste bytes over there. So we can encode it with the mantissa and an exponent representation. And also somehow, this kind of the contrary function of the address compressed and byte compressed. Somehow you need to tell the circuit to store this mapping between an address and an index and a 32 byte and an index. So we have these functions in order to tell the circuit that, hey, store me that into this sparse Merkle tree. This regarding the first is regarding the address, the second one is regarding the 32 bytes. And well, while we were iterating over this function, well, we realized that in Solidity, when you do the AVI compiler, if you, in the function of Solidity, if you define like an array, bytes, or a string, normally the Solidity just put, it does a path write to 32 bytes, so we reserve just one function in order to improve this data availability. Here there is an important thing, which is an extra rule. What if we found some of these functions inside the data transaction field? As you know, Solidity, basically, when you call a smart contract function, you have the selector, and then you have chunks on 32 bytes, depending on the parameters that the function has. So if we find any of these functions inside the data, then we will path left to 32 bytes. Okay, and in order to understand it better, what about an example? So here is a standard ERC20 token transfer. This is all the standard transaction fields. This is a legacy transaction. And this is basically the RLP encoding that maybe you are very familiar with. First is the RLP list header, the nonce is 0, gas price, we have a header of 1 byte, and then read 4 bytes, gas limit exactly the same. The 20 bytes for the address and 94 in order to read these 20 bytes. The value is 0, selector inside the data, then the 2 with is padded to 32 bytes, then the amount, which is exactly the same, and the chain ID. Okay? And at the very end, this is about 109 bytes. So we are going to do the same exactly with the function that we saw at the very beginning. We need to somehow say which fields we are going to read. So for that, we define a transaction type, which is 1. This is a small value, so we'll use the function of a small value. And then if we encode it at the very end, it's just 1 byte. Then we have the nonce in 0. Again, it's a small value. So this is very straightforward. It will be just 1 byte. Then we have the gas price. The gas price, you can represent it as mantissa and exponent thing. So if you use the function of the value compressed, at the very end, it will be just 3 bytes. This is the gas limit, again, exactly the same as the gas price, 3 bytes. And this is where the compression comes. This is the 2. Imagine that in the address tree, you have this address, the 2, associated with an index of 4. So instead of just putting all the address, you will put just 1 byte because it's a reference to the index in the address tree. Okay. Then you have the value, which is small value, it's 0. Then here you need to say how many fields are you going to read inside the data in order to apply this 32-byte padding to the left. So here, basically, there is the first number that will be like we are going to read 3 fields. So it's the 43. And then the selector, which is basically reading 4 bytes. And in order to do that, we use the very first function call. Regarding the 2, this almost happens the same with the 2. This is a transfer, ERC20 transfer. And here the 2 is 32 bytes, but at the very end, it's an Ethereum address. So this Ethereum address, if we assume that it's inside the address tree with a mapping of an index 12, we can basically represent it with just 2 bytes. And remember, if we found this function inside the data, it will be padded left to 32 bytes, okay? The data amount, I just put an example of 100. You can code it with this kind of function of data less than 32 bytes. So at the very end, it will be just 2 bytes. And the same happens with the chain ID. Okay. Then, well, the squares are a little bit moved. I don't know why. But at the very end, we move for 109 bytes to 24 bytes at the very end. So the reduction, it's important. Well, here is a summary of all the data strings that I present. And basically, in an Ether transfer, for example, we move for 111 bytes to 16. And we can see, I mean, we did some testing regarding a very standard transaction types, I would say. And the reduction is about 7.5x, which is, I think it's quite a lot. If we put that all together with the EIP 4844, which the data ability that you put on chain, it will be kind of we will have some 5x gain. At the very end, if you remember the table at the very beginning, which the data availability cost was about 95% of the cost of the layer 2 transaction, now it goes down to around 35%. So now we have to put more focus on the sequencing part and to do some gas optimization regarding this layer 1 smart call. And that's it. Thank you very much. Do we have time for questions? I don't know.
We have 2 minutes for questions. If anyone has any questions, there should be someone with a microphone roving around.
Oh, well, I lose
see no microphone roving around, so you can borrow mine.
Yeah, thanks for the great talk. I'm curious how you handle the, dropping the signature, because as you said, you have to prove it, so you have to provide it in the witness, right? If the prover and the sequencer are different entities, how do you incentivize the sequencer to share this private data, the signature, with the prover?
I mean, the sequencer does not need to share that at the very end, because the sequencer provides the snark proof, and then it's verified inside the circuit. At the very beginning, I mean, the sequencer and the prover is kind of the same person. I mean, okay, I understand what you mean. Both of them are hand by hand. I mean, one will be stop the other and the other way around. So they need to kind of collaborate. They need to share data, I would say.
Okay, maybe time for just one more quick question.
Thank you for your great talk. And I have a question about the data compression. You mentioned that you use the parameter types and use a address tree and data tree. So I guess this data compression only applies to those calls to open source contract, I think, because you need to get the API of the contract and decode those parameters.
It's not necessary.
No,
because at the very end, Solidity just do, I mean, the AVI compiler just do, I mean, in the data section, you can find random bytes over there. If you find random bytes over there, it's totally okay. I mean, you will not be able to compress, but you will be able to read it with the very first function that I present, the one that you read more than 32 bytes. But here is that when you call a smart contract call, and there is a definition of the parameters over there, then you can split in chunks of 32 bytes. So you are able to compress. But otherwise, it will be very difficult. It's basically depending on the data field.
Okay, thank you very much, Carlos Matallana.
Thank you.